Hello, welcome to the continuation of calculus. The first video we studied about first principle of differentiation, and this we are going to look at the other ways of differentiating a function, and so want to look at power rule. With the first principle, we saw that if I give you x squared plus 1 and you want to differentiate using first principle, it's very simple. You have to go by the first principle formula. And we saw that from the first principle, the differential of this dy dx is equals to 2x. We also saw another example as y equals 2x squared minus 3, and the dy dx gave us 4x. Now, what if you are given a function like this? 2x cubed, 4x squared, 3x plus 1, and you want to use the first principle. You realize that when you expand this one using the first principle, you get a very lengthy equation. And due to that, it becomes more difficult to handle. And so mathematicians realize that if the function becomes more complicated, using the first principle will always make the work difficult. And so they find a way of doing it in a very simple way. And that is the idea of the power rule that was established. And power rule can also make some of these functions very simple. But yet there are other functions that power rule will make it more difficult. But you have to introduce a new set of rules. And so we have power rule, we have quotient rule, we have product rule, we have implicit and stuff. And we'll be looking at all those things. So first of all, let's see what power rule entails. With power rule, if you are given a function like y is equals to x to the power n, if you find the derivative, it will be n multiplying the function, then n minus 1. That is the power rule. And so we can differentiate term by term of every function given. But before then, let's see how this formula came about. How did it happen? We want to prove this using the first principle. Then we'll take series of examples. Let's say we are given a question to differentiate a function x to the power n with respect to x. So here there should be respect to x. And we want to go by this. That's the first principle. Now with the first principle, we know dy dx is equals to limit as h approaches 0. Now I want to write the function x to the power n. And so we say x, whenever we see the s, we put s plus h, like we did earlier. So to power n, then minus the whole function again, that is x to the power n, all divided by the h. And this is what we write. So we expand this one to the power n. This will be equal to, that dy dx will be equal to the limit. Remember, we've not taken the limit, so we have to keep repeating the limit. When I expand this, I'm going to use the binomial expansion. And if you've forgotten the binomial expansion, you need to go back or search for the video on binomial expansion and then go through. There is a video for that, so you can learn that one. So we'll use the combination approach since our n is a natural number. And so the first term for expanding this one is going to be n combination 0 s to the power n. Our h will be to the power 0, so it will appear, plus n combination 1. Remember, the n combination 0 and n combination 1 and the rest are the coefficient of the expansion. So x will take power n minus 1, then h will take power 1, plus n combination 2, s will take n minus 2, and then h will take power 2, and this will continue until the last term is going to be what? Let me write it here. The last term is going to be n combination n where the s will no more take any power because it will take power 0, and h will take the last power of n. This is how the whole thing is going to look like. So by typing it, to make it very easy for you to see. So the first one, we saw this, and then the second term, n combination 1, n minus 1 for the s value, and h will take power 1. The next term, s will take power n minus 2, and h will take power 2. The next term will go that way until finally we get to this term where the n will take combination n, and s will not come again, but the h will take power n. Then minus our original function, because from here we saw that the function, the whole function minus the function again. So everything here is what we have here, and then this part represents the function here, all divided by h. Now you can see that if you look at the first term here, n combination 0 is 1. And so that's going to leave our function here, or our term here, to be x to the power n. And we have minus s to the power n at the tail end here. And so that could be subtracted. What I mean is this. So we will have this left, and then this is the same as what we have here. So this will die with this, leaving out with the middle part of the equation as this. So you can see that here we are left with the n combination 1 s to the power n minus 1, then h, then n combination 2 s to the power n minus 2, then h squared, plus n combination 3 s to the power n minus 3, h cubed, until the last term will be this one. Now let me try to factor the h out from here. If I factor h out, I'll be having n combination 1 s to the power n minus 1, and h will not come again here. Then n combination 2 s to the power n minus 2, and h will reduce to 1 from here, plus n combination 3 s to the power n minus 3, h will reduce from 3 to 2. And this will continue until the last end, h will reduce to 1. So we have this as the outcome. Now since we factor h out, this h can cancel this, leaving out with everything in the middle. Can we see it? So we'll have this as the outcome. Now h has cancelled with this one. This is what we have. Now I cannot take my limit since I don't have a denominator of h. And the limit as h approaches 0, it means dy dx will be equal to, there's n combination here, I think that has gone off. So I'll be left with n combination 1 x to the power n minus 1. Okay. Then I have h approaches 0 means whenever I see h, I put 0 there, which h to the power 0 is 0 to the power 0. So 0 to the power 1 is same as 0. Everything will go to 0 here. This will go to 0. This will go to 0, leaving out with only the first term. And here we will see that this implies that dy dx is equals to, what is n combination 1? Any number combination 1 is the same as the number. So n combination 1 is the same as n. X n minus 1 will be the final differential of the function given as y is equals to x to the power n. And so this is how this particular formula came about as the power rule. So this is power rule, and this can help us to simplify every function if you want to find its gradient or want to differentiate a particular function. Let's go ahead and solve series of examples using the power rule. Example 1. Find the gradient of the function this. Remember, we've already done this using the first principle. And the first principle, we saw the answer to be 4x. Now, here with the power rule, we differentiate term by term. And so the first term, that is 2x to the power 2, is the first term. Then we look at the second term as negative 3. So for the first term, based on what we've just established, that if I have this, it means multiply the exponent by the coefficient here, then subtract 1 from the exponent. That is what we've established. And so if I have 2x to the power 2, if I differentiate it, I'm going to have 2 multiply the coefficient, which will give me 4. Then I subtract 1 from the 2, then I have x to the power 1. You get it? That is what we are going to apply. So now let's solve the question. So to find dy dx, we'll have 2 times 2, 4, then x to the power 1, which you can choose not to write the 1. And then to the negative 3, remember that negative 3 here means there is an x to the power 0 to it. But normally we don't write it. Every constant is having x, a variable x to the power 0. And so the variable x to the power 0, 0 times the negative 3 will give me 0. Then x to the power 0 minus 1. And everything here will be what? 0. So I'm going to get plus 0. So I can choose not to write it, but I'll write 4x. And that is why the answer gave us 4x from the onset. Example 2. Find the derivative. Example 2. Find the derivative of the function y is equal to 3x cubed plus 4x squared minus 5. And once again, we do power rule. And so term by term. The first term, we have 3 times 3, which is 9. X to the power, then we subtract 1 from the 3, and we get 2. Plus 2 times 4 here will give us 8. Then x to the power 1, which you can choose not to write it. Then minus or plus 0, because a constant term will give you 0, like we saw earlier. And so finally, this answer becomes 9x squared plus 8x. And that is the result for the differential of this. Example number 3. You can pause the video and try your hand on this. When you are done, you can resume and check your solution with what I'm going to do. I believe this is how your solution came about. So dy dx is equals to, you multiply the coefficient by the constant, the exponent by the coefficient, and that will give you 6x to the power 2, right? Plus, you multiply the exponent again, that is 3 on 2 times 4, and 3 on 2 times 4 will give you 6x. Then we subtract 1. So that will give us 1 on 2, right? Okay. Then we say plus, looking at this one, 1 over 4 times 2 will give us, then that will be 2. That will be 1 on 2, right? X, then we subtract 1 from 1 on 4, which will give us that's negative 3 on 4, right? So this will be the result of our first differential of this particular equation. Okay, so we can leave our answer this way, or we can write the exponent in terms of square roots, but I presume this can be done as our final answer. Example number 4. You have to find the derivative of the function this. And this is a bit complicated function. You see that if you have to use the first principle for this, it won't be easy at all. But with the power rule, it will be very cool. This is what I will do first. The function is this. And so I'll first have to divide everything here by the denominator. So I can say 4x cubed 2x squared 10x squared 2x squared 6x 2x squared. So what it means is that because everything is divided by this, you can keep them in individual terms like that. And so when you simplify, we have 2 to the power 2x here to the power 1, and the whole of this will die with this, so I'll have 5 plus, here's power 2 and here's power 1, and then 2 can divide 3 is 6 as 3. Then I have divided by x, because the s will be denominator, it won't be numerator, because the here is power 1, here is power 2, so the s will go down. So the whole function can be rewrite as 2x minus 5 plus 3x to the power negative 1. This is how the whole function is going to look like. Now I cannot differentiate the function. Now remember, this name is j of x, it's not y. So instead of saying let y be equal to this and say dy dx, I can just say j prime of x, which represents the derivative of j, the same as saying dy dx. So I can write this one to represent the derivative. And so I'm going to differentiate. Here is power 1, so 1 times this will give me 2. Then 1 minus 1 is 0, so s to the power 0 is just 1. And so the answer there will be what? This. Then minus, if I differentiate constant, I get 0. Then this negative 1 times this will give me negative 3x. Then minus 1 will be negative 2. And so this is the answer, or I can rewrite this as so we can write it this way, or we can say 2 minus 3 on x to the power 2. Should I leave your answer this way or that way? It will be the same. So that is how we handle power rule. Go ahead, get a lot of questions and try your hand on them, and I believe you will get over it. The next thing we want to look at is product rule. We've looked at power rule. Power rule helps us to make some of the work very simple. And so product rule also will help us to simplify some complicated functions. And product rule says that if we have y equals uv, where u and v are two functions, then dy dx is giving us this. You hold the function u, then you differentiate the v, plus hold the function v and differentiate the u. If you are given a function like y is equals to, let's say, x squared plus 1, 2x cubed, maybe minus 5x plus 3. Now, functions of this sort, you realize that if you want to use the power rule, you need to expand the whole function before you can expand term by term. Sorry, you can differentiate term by term using power rule. And you see, mathematicians always want something simple. And so they deduce this rule called product rule, which will help you to do this without going through the expansion. And so what you do is that you hold the first term or the first function by letting it be the u and letting this one be the v. You hold the first one, you differentiate this. Then when you finish, you add by holding the second one, that is the v, and differentiate the u. And so we'll see example on how these things work. So let's take one example and see. Example can be this. We have to evaluate the function with respect to x, this. There are so many ways of writing a question for differentiation. So another form can be this. You can just write this and say evaluate. Okay, so we want to evaluate this. So to evaluate this, what we do is that we let maybe u be the first function, 2x plus x squared. Then we differentiate u with respect to x. So we have du dx, and that will give us, here's power 1, remember, power 1 for this one. So 1 times 2 here will give me 2, then minus 1 will give me 0, and so the whole of s will be power 0, which is x, which is 1, sorry, plus when you differentiate x squared, you have 2x. So that is the first one. Then we let also v be equal to the second function, 3x minus or plus x cubed. Then we differentiate v with respect to x. So we say divine dx, and that also give us 3 plus 3x squared based on our power rule. Now for the formula for power product rule, so for the formula of this, that is dy ds is u divine ds plus v du dx. It means that my final answer for dy ds is going to be the original u, which is 2x plus x squared, times the differential of u, which gave me 2 plus 2x, plus, that's the formula plus here, and then I'll hold the v, which originally supposed to be 3s plus s cubed, times the differential of v with respect to s, which is this one, 3 plus 3x squared. And so you can simplify this, and that becomes your result. And when you go through the simplification, your answer is going to be this. You expand this and that, and you expand this and that. So do that on your own. I want to give you the answer finally because I wouldn't get a space to do all the lengthy expansion. No, I think the arrangement is wrong. Let me repeat this part of the arrangement again. So per the formula, the u, which was 2x plus x squared originally, times the differential of the v, rather, so to be 3 plus 3x squared, then plus, then I have the v, which is 3s plus s cubed, multiplied by the differential of the u, 2 plus 2x. So you cannot expand this. So your final answer, when you do the expansion correctly, you have 12x, 9x squared, 8s power 3, then 5s to the power 4. So this should be your final answer for the derivative of the function given. Example 2. You can pause the video and give your hand a try, or try your hands on them. Here, if you let u be equals to 2x power 3, then du dx will be equal to 6x. Right. And if you let v also be equal to the function this, 5x squared plus 2s to the power negative 2, the differential of v with respect to x will be equals to 10x minus 4x minus 1 here. For this one will be negative 3. So then, using the formula once again, we have u being 2x, so this equals to 2s cubed. We'll multiply the derivative of this plus, then the original 5x squared plus 2x minus, minus 2, we'll multiply the derivative of that, which is 6x. So when I expand this will give me 20x to the power 4 minus, remember we are going to do this times that. The 2 times 4 will give me 8, and s power 3 times s power negative 3 will be negative s to the power 0, which will be 1. So every term over there will go off. Then plus, when I come to this side, I have this to expand with this, which will be 30 s cubed, and this times that. Remember, this is negative here, and so that will give us plus 12 s to the power negative 1. So this will be your final answer for that. Sometimes if you're not maybe conversant with the formula work, you can simply expand this and use the power rule, unless they specify that they want to see you using the product rule. You can expand and simplify and then use the power rule, or you can go by the product rule, and I believe that will help you. Okay, so you try this example on your own. Example number 3. You can do this by expanding the whole of this if you want, and then later simplify and use the power rule, or you can let your u be this, v be this, and then use the product rule. So try your hand on it. Okay, now let's go to the final rule for this very part of the differentiation, that is the quotient rule. So the next rule is quotient rule. Now, the more complicated functions gets into, more rules are being generated every now and then to simplify it, to make it very simple. And this time around, when you have a function, let's say u over v, which of course we have the u as a function and v as a function, this becomes a rational function, a function over a function, where the denominator function will never be equal to 0. Then the formula for the quotient rule says that dy dx is equals to, you hold the v, the denominator first, you differentiate the numerator, minus hold the numerator, differentiate the denominator, then divide everything by the denominator squared. It looks a bit complicated, but as you take examples, this is very easy to understand. Let's take example and see. So example number 1 under quotient rule. Here we are to find dy dx given the function x 2x plus 1 on 2x minus 2. And so once again, we can let the numerator be u and the denominator be v. You can also go other way around, but when you go other way around, then the formula will change, because always hold the denominator first here before the numerator will come second. And note that since subtraction is not commutative, if you interchange the position, you might get it wrong. So if you keep the u up and the v down, then this is the formula. But if you keep the v up and the u down, then here will turn into u, this will turn into v, and the down one will turn into u. So take note of the arrangement of the formula, right? But for product rule, that one you can arrange it the way you want it. That one, because addition is commutative, whether you bring the u first or the v second, I mean, to be the same. Okay, so let's see how we will handle this. So here I will say let u be equals to 2x plus 1. Then when I differentiate u with respect to x, I have 2 as my answer. Then when I say let v be equal to the denominator, which is 2x minus 2, and I say divine dx, here too I'll get 2 as my answer. Now using the formula says that I should hold the v, differentiate the u minus hold the u, differentiate the v, and divide everything by the v squared. And so using that formula, I would say my dy dx will be equal to, I will hold the v, and the v is 2x minus 2 times the differential of u, which is 2, minus hold the u, and the u is 2s plus 1, then times the differential of v, which also gave us 2, all divided by v squared. That will be 2x minus 2 all squared. Then you simplify this to be your answer. Of course, this can be simplified as, so I have 4x by expanding this one, minus 4, then minus 2 times this will give me 4x minus 2, all divided by x, 2x2 squared. Now, at least 4x minus 4x here will be 0, leaving out with negative 6 for the numerator side, all divided by 2x minus 2 on 2. So this will be the final answer. You don't need to expand the denominator, since its expansion wouldn't have anything to do with the work, because the numerator cannot be used to divide. And since we have only negative 6 at the top, we can leave our answer as such. So that is how we use the quotient rule in finding the differential of a function. Example number 2. So for example number 2, we are to find the derivative of this with respect to x. So once again, I will define the numerator as u, and that is x squared minus x plus 1. Then when I differentiate that with respect to x, I have 2x minus 1. Then the denominator will be defined as 2x minus 3. Its derivative will give me 2. Then using the formula, so my v, original v, is 2x minus 3. So that will be 2x minus 3 times the differential of u, 2s minus 1, minus the u, x squared minus s plus 1, times the differential of that, all divided by the v, which is 2x minus 3 all squared. So you can simplify this by expanding 4x squared, then this times that, negative 6x, minus this, we did this and this, which is 4x squared, then this and that rather. So 2x minus this will give us negative 2x here. Then we come to 3 times this, which is negative 6x. Then this times that will give you plus 3. Then minus 2 times this will give you 2x plus 2x squared here, and then minus 2. Remember that this is negative affecting everything here, so it will affect this one to be negative, this to be positive, and this to be negative, all divided by our denominator, 2x minus 3 all squared. So we can simplify the numerator once again. So we have, note that this can die with this because this is minus and this plus. Then we have, so this 4x squared and 2x squared will give us 2x squared. Then we have negative 6x here. Then this and this will give us plus 1, all divided by 2x minus 3 all squared. So this could be your final answer. You can see that the numerator, we can't factorize it. If we can factorize it and the factors can cancel, then we cancel and simplify further. But since 2x squared minus 6x plus 1 cannot be factorized, we leave our answer as such. So dy dx is equal to this. You can try your hands on example 3 and example 4 and just play with them, and I believe you can do this. So we'll let this one end the video number 2. So expect the next video, which will take you through chain rule and then implicit functions. And probably if you get a time, then we'll look at another aspect before we end video number 3. So for now, this is part 2 of the differential calculus.